Science time. Today we're talking about seasons. Let's just call it seasons. There will be more in this, obviously, than seasons. You first learned about seasons when you're not even in kindergarten, probably. You haven't even attended formal education when you start learning about seasons. So I'm not going to ask you questions like, what kind of things happen in the summer? We know what the seasons are like, but we're going to talk today about why there are seasons. Let's begin by diagramming. Okay, focus up, Gabriel. Focus up. Shh. Okay, so we're talking about the reason that Earth has seasons. So let's start with a little diagram here of the sun, and we're going to draw Earth's elliptical orbit around the sun. Does this line exist in real life, Aaron? No, this is an imaginary line so we can better visualize the way it is. And let's draw from the top too. I'm going to draw a more oblate circle. In real life, Earth's orbit is almost entirely circular. It's not quite a perfect circle. I'm going to draw it with an exaggerated ellipse so that I can demonstrate my point better. There's a statistic that I read online that I don't remember the number. Some ratio, 4/5, I'll say. I don't know if that's true. You can look this up. 4/5 of the graduates from Harvard Business School, or Harvard Medical School, I can't remember, but some college of Harvard, Harvard, a well-esteemed university, some college of Harvard, the graduates of that had a misconception about why Earth has seasons. And most of those people, all of those people that had it wrong, thought that it was because of this wrong thing. So here we're going to label this misconception. What does that mean? If I've misconceived something, what does that mean? In layman's terms. Yeah, I got it wrong. I'm wrong about this. So here's the misconception. Here's the wrong thing that people think, but they're wrong. So is this going to be the right thing, Dalton? No, this here's going to be wrong. This here's going to be wrong. People think when they're wrong, when they're young and also wrong, but wrong nonetheless, they think that Earth is close to the sun. 6 inches. When Earth is close to the sun, it's summer. And when Earth is far from the sun, 9.5, it's winter. Do you see why people might be able to think that? Why would people think this? It's easy to think this. Wrong. It's a misconception. It's wrong. Why do people think this, though? Here's why people think this. Because in your daily life, if you're at a campfire and you're close to the campfire, it's warm, like summertime is warm. And if you're far from the campfire, it's cold, like wintertime is cold. But that's wrong. Is this right, Fate? No, this is a misconception. It is wrong. This is wrong. In fact, in the northern hemisphere, it is the exact opposite. In this, Earth is at its what we call periapsis. It's at the closest point when the north would be somewhere in the middle of winter. So this is wrong. 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 Shh. Wrong. So what really causes seasons? So we know this is wrong, or hopefully we now know it's wrong. But what is right? What really causes the seasons? Yeah, exactly right. The tilt. The tilt. Shh. So what happens is Earth has a tilt of its axis. We talked about this in the last video, so this will be mostly review, and you can watch the last video if you need to. But Earth has a tilt in its axis. Someone remind me, in degrees, what is the axial tilt of planet Earth?
23 degrees.
Angle theta here equals 23.5 degrees. It's a little less than 0.5, but 23.5 degrees. And then we also know from the last chapter, what here, if I shade one side of this, that should make this question really easy. What here on my diagram over here is nighttime?
The dark side.
Yeah, this here is night, and this here is day. And we also know that the sun, even though it behaves mostly as a point source of illumination, its rays end up being roughly parallel to planet Earth. Where's the equator on this diagram? Should I draw it perfectly across like this? No, and now I wish I didn't. But it should be at the same angle, 23.5 degrees. That's the equator. That's the equator. Same thing here. What do we call What do we call this red shaded part of my equator, or above the equator, north of the equator? We call this the northern hemisphere. Okay, let's have a little close-up here. At this time, where we have here on the left side of our diagram, don't label it left, but on this side of our diagram in figure 1, and we'll call this over here figure 2. Here in figure 1, let's draw a little close-up of, if you here have your house and your garden and everything, here's you. I'm going to straighten this out. Looking at, we're focusing on this, and we're straightening it out. Here's your little house and your garden and your dog. Looking at this, where is the sun relative to my, where's this, looking at this little, and looking at this, how is the sun going to appear to be in my sky from here? If this is me, here, this is what I look like. If this is me, what is, if this is me, where is the sun going to appear to be in my sky? Yeah, so we'll say for this diagram, we're going to say above. The sun's rays are coming down parallel because the sun appears to be above me in the sky. Okay, now let's do the same thing over here. I'm going to erase my misconception. Get out of here, misconception. I'm going to do the same diagram in red over here. Here's my house. I'm still in the same spot. I'm still in the daytime side.
Your house is tall, though.
Here's my, yeah, okay, but it's not to scale. Here's my house again. Here's my garden. Here's my dog. Be quiet, please. Here's my body. Where's the sun going to appear to be in the sky now?
It's going to be a little over.
A little over?
It's going to be like over
A
here.
lot of it.
A lot of bit over. It's going to be over here. The sun's rays are still parallel. If I draw, even if I, just in my diagram, you do this in your lab, even if I, in my diagram, space these roughly the same amount, you can see in this one, the land, the top of my head, my house, my dog, my garden, all of it is receiving more sunlight per area. Yes, do you see that? In this one, less of it is receiving, or it's receiving less sunlight per area. How should we label this season? And how should we label this one?
It's spring. No.
Winter.
And Kesslin points out these two that are here.
Spring and
Spring and autumn. So, for the quarter of the year, roughly, for the quarter of the year that the Earth is receiving the most sunlight it can, if we divide the year into 4 quarters, for the quarter that's receiving the most sunlight, we call that summer. For the quarter that's receiving the least sunlight, we call that winter. In between summer and winter, we have fall. And in between winter and summer, we have spring. Okay, that's the seasons in a nutshell. So in a complete but brief sentence, why does the Earth have seasons? You say, here's your sentence frame. The Earth has seasons because... The Earth has seasons because of its axial tilt. Because of its axial tilt. So that's the sun, but what else would change about the sky throughout these times? Are we still going to have moonrise and moonset and the phases of the moons and things like that? So here, what we would witness from planet Earth is a different relative elevation, a different elevation of the sun. This one has a higher elevation, and this one has a lower elevation. This angle theta here is smaller than this angle theta prime here. Theta prime is greater than theta in this case. So we notice a different elevation of the sun. We still have the same moonrise and moonset because remember the moon's phases are due to the orbit. Stop talking and pay attention. Stop talking and pay attention. The moon has phases because of the moon's orbit around the sun, which is independent of this cycle. The moon continually orbits around Earth throughout this series, independent of the Earth's rotation about the sun. So the moonrise and moonset would still be the same. Okay. But what would we also notice different? Is this is the only thing, this is the entire universe here? No. What am I drawing now?
You're drawing the stars.
The stars! Yeah, the stars. I'm just going to start using a different color for this little section here. The stars. And how do we divide up, by the way? We divide up the night sky using the stars into constellations. And you may not be aware of this, but if we think of individual stars like cities on a map, the constellations are kind of like states. The states are continuous, where the cities are discrete. So even though the constellations are said to be made of certain stars, like I could draw, we could pretend this is Orion here. It also is it is the main thing in this whole area. So we divide the night sky, the whole night sky. There's no part of the night sky that's not divided into areas. And so the whole night sky is divided into these areas called, we could call this constellation Orion. Don't at me. Comments are disabled for this video. But you can see here was the night side of planet Earth. Here, you need to stop talking and pay attention. Here was the night side of planet Earth. And here's the night side in the wintertime. What else will be different? Not just the elevation of the sun between the seasons, but what else, looking at my new additions to the diagram, yeah, we will see different constellations throughout the year. So we see different constellations throughout the year. We have, in both the northern and southern hemispheres, we have winter and summer constellations. But we also have these what we call circumpolar constellations, which are those that are around the poles. Polar, they're circumpolar. We see them all year long. They're all year, the poles. We see the circumpolar constellations. So in the northern hemisphere, we always have these certain constellations: Aurora Borealis, Ursa Major, Ursa Minor, Cassiopeia. All those constellations we always see all of the time because they're around the pole in the northern hemisphere. However, people in the southern hemisphere never see those constellations. They instead see their circumpolar constellations, but I don't even know because I don't live in the southern hemisphere. So the constellations change throughout the year, but there are some constellations that we always see. What constellation do you expect what star do you expect we might always see in the northern hemisphere? The North Star. The North Star Polaris, which is part of the constellation, no, Ursa Minor, the small bear, but people call it the Little Dipper, but they're wrong. And then these ones that change throughout the year are part of the constellations of the zodiac. They follow the same path that the sun does through the sky. Those are the zodiac constellations. And coincidentally, the constellation that the sun is said to be in, the constellation the sun appears in it'd be the daytime sky because the sun makes the daytime. But the constellation that the sun would be in is what your star sign is when you're born. All that, of course, is garbage. None of that has any bearing on who you are as a human being. But the zodiac sign that the sun happens to be in when you're born is your star sign. So when you say, hey girl, what sign are you? What she's saying is where the sun was when she was born. In what constellation the sun was when she was born. Be quiet, please. Be quiet, please. Okay, so now let's get into the stuff that you already knew from when you were a little kindergartner. What are some, very briefly, because you already know this, and stop talking, and what are some differences you notice in this diagram in real life and this diagram? This is going to be the messiest board I've ever done. What are some differences between these two things, between the summer and the winter? Very briefly, because we already know this. Temperature, yeah, it's hot, we go swimming, beach balls, we go fishing. In this one, we know Christmas time, Santa Claus, snow. All those are different, but why are those different? All of that comes down to what? What thing on this board already? No, not the tilt. We don't call it tilt. The elevation of the sun. You mean the tilt of the earth, but yeah, the elevation of the sun. The relative elevation of the sun is why we have all these differences. So your book goes into why flowers, or why plants, not just flowers, but why plants, how plants know. How does the grass know to green up? What is changing about this throughout the year? The temperature? No, not the moisture. The amount of sunlight. The genes of a plant have an inborn growth cycle that begins when the day length gets to a certain amount and ends when the day length lowers to a certain amount. The spring and the fall, that is. It ends. Last thing we're going to talk about real quick are solstices and equinoxes. Solstice, meaning what? What's a solstice? Define it.
The solstice is either
Okay, one person.
shortest day.
Solstice, yeah. The solstice is the highest or lowest.
Who just farted?
Taylor, please write your name on the board. The highest or lowest ratio of sunlight to night hours. When will we find these? Specifically, the highest would be during what season? The highest ratio of sunlight to nighttime would be summer. So we have a summer solstice, which is also when we say the summer begins. So really, this is the beginning of summer. No, it's June, and it's June 21st, I think. But yeah, you're right. June, July, August, and then the first part of September, or actually, I should say, the last part of June, all of July and August, and the first part of September comprise summer. They begin at the summer solstice. What about the lowest ratio? Winter, which begins at the winter solstice, the 21st-ish, I think, of December. And so then the end of December, all of January, all of February, and the first part of March are winter. And then we also have these equinoxes.
What?
And what would be an equinox? The singular of this is equinox. What would be an equinox? I spelled it wrong. Yeah, so the equinox is when the daylight and night hours are the same. So the ratio is 1-to-1, are the same. And these begin, we have the vernal equinox. Vernal equinox is spring. And the autumnal equinox is fall. And so the vernal equinox is March 2nd, Kesslin says. I think, is that right, Kesslin? And that's the beginning of spring. So the end of March, April, May, and the beginning of June are spring, which begins at the spring equinox, the vernal equinox. And then the autumnal equinox, which begins September, or which is September something, 21st, I don't remember the date. So the end of September, October, November, and the beginning of December are fall. Okay? Do you have questions about any of this? This is, like I say, this is one of the most crazy psychopath diagrams I've ever done. But you followed as I went along, right?
Yeah.
And you wrote down the things that were important? Do you have questions before we end this? Several people had questions that they were very willing to shout out right in the middle of me trying to talk. So please ask your questions if you have them.
Who threw a piece of gum at me?
That does not relate to this.
That is rude.